An example using torque is Atwood's machine, and this time we'll do it with a real pulley instead of a massless pulley. Usually you model the pulley as a disk, so we'd have a moment of inertia, 1/2 times mass of the pulley times r squared. If we look at the free body diagram, all the forces acting on these things, we see the usual M1G on mass 1. The tension this time is labeled T1 because it won't be the same as the tension holding up the second mass. We have on M2, T2 and M2G, and then on the pulley we've got its mass, the normal force delivered through the axle holding the pulley to the wall, and T1 and T2, notice they're pointed downward from the pulley's perspective where they were upward from the masses. We have no x forces anywhere, so if we apply Newton's second law, we get that T1 minus M1G is M1A1Y. For mass 2, T2 minus M2G is M2A2Y. We can do this same thing for the pulley, the Y version of the forces, and it will give us that the normal force equals the weight of all three things, pulley and both masses. Acceleration there is 0. This is true, but it's not useful. It doesn't help us solve anything, so we keep moving. The only thing left is torque. The normal force and the weight of the pulley, MPG, don't produce torques because they act through the center of the pulley. The tensions, on the other hand, will produce torques. And if we define a clockwise torque as positive, we see that T1 will be trying to pull the pulley counterclockwise. So it would be negative, T2 will be positive. So the torque from tension T1 is negative T1 times R, the radius of the pulley, times sine theta. Theta is 90 degrees because the point of application of the force is the far left of the pulley, and the tension points down from there, so we have a 90-degree angle. For T2, we get almost the same thing, except this is a positive torque, so we get T2 R sine theta, which is just T2R. Sum of the torques is I alpha, so we can write that T2R minus T1R is I alpha. We can plug in what I is for a disk, and then we can cancel the R's. A little bit of sloppy notation here. This lowercase r and this uppercase r, they're both the radius of the pulley. So we cancel one and we're left with this. T2 minus T1 is 1/2 mass of the pulley, R alpha. Problem is we have 5 unknowns. We don't know T1, T2, alpha, A1Y, or A2Y. If we say that the rope moves without slipping on the pulley, then we'll have R alpha equals the acceleration. That makes some choices for us, though. Since we've said clockwise torques are going to be positive, clockwise angular accelerations also have to be positive. So this means if the pulley is turning clockwise, we consider that positive acceleration. That would mean M1 is moving up, so A1Y would be positive and A2Y would be negative. So this choice of clockwise torques as positive has forced us into A equals A1Y equals negative A2Y. So we make that substitution in our 3 equations that we've got so far. We can write T1 as M1G plus M1A, T2 is M2G minus M2A, and then T2 minus T1 is 1/2 MPA. We plug in for T2 and T1 from these formulas, and after a little algebra we get that A is M2 minus M1 over M1 plus M2 plus 1/2 MP times G. Notice this is what we would get for moving all 3 of the masses, except because we're just rotating the disk, it's equivalent to moving half the mass. When we're doing problems in general, we should always get the same answer whether it's Newton's second law with forces and torques or conservation of energy. If you remember from a previous lecture, we had the final speed of an object rolling down a hill. We used a weird hill, but we could have used a regular inclined plane, and that'll make it easier to compare with the torque method. For a disk, we found that the speed of the bottom of the hill was square root of 4gh over 3. If we want to do this with forces and torques, we look at all the forces we see here. We've got the normal force, we've got mg. Notice that we have to have a frictional force acting up the plane, or this won't roll down the plane, it'll just slide down the plane without rotating at all. Also, this problem never said the disk was about to break traction here, so we don't know that Fs is equal to Fs max. We just have to leave it at Fs. We make our usual coordinate choices for a plane, and we say that x is along the plane and y is perpendicular to the plane. That way we know there's no y motion. And we get these three equations. And of course we have torque. So if we look at the x forces first, we have Fs pointing in the negative x direction up the plane, mg sine theta pointing down the plane. Those two together give us max. Then there's nothing going on in the y direction, at least no acceleration. So we know that we're going to get n equals mg cosine theta. We can't do much with either of these two things right now because we don't know if Fs is equal to Fs max. Ordinarily we would plug in mu s times n, but we can't say that. This is the problem with friction, if you remember. Usually when we've had a problem like this, we've said we're about to slip, so that Fs really is Fs max, and we can make this substitution, but we're not doing that here. For the torques, we know we won't get a torque from either mg or n because they both act through the center of the disk. The only thing that gives us a torque is friction. So if we again pick clockwise torques as positive, we get that the sum of the torques is I alpha, and we have Fs times R. Again, we have a 90-degree angle between Fs and the rotational axis and the point of application of the force. So the sine theta disappears. So Fs is I alpha, we plug in what I is, and we cancel an R, and we get that the frictional force is 1/2 mr alpha. So the disk rolling down the hill is clockwise motion and motion in the positive x direction. There's no slipping, so R alpha and Ax are both positive, and we can replace them with A. We plug in Fs is 1/2 ma into our x equation for forces, and now we get something we can solve. We get that the acceleration is 2/3 g sine theta. Now, if we really want to find the velocity, we have to use kinematic equations. And we'll use this one, where v final squared is v initial squared plus 2 times the acceleration times the distance. Our initial velocity was 0, and the distance is the length down the plane. We can connect the length down the plane to the height of the plane by realizing that L sine theta equals h. So we're going to write L as h over sine theta when we plug it in here. So we get v squared is 2ah over sine theta. We just found a is 2/3 g sine theta. So we get just what we had before. V is square root of 4/3 gh. One thing that might have occurred to you, why are we using friction in this force method, but we didn't mention any work done by friction in the energy method? The reason is there is no work done by friction. It's present and it allows the disk to roll, but because the point of contact isn't moving relative to the ground, we don't have any displacement, and that means there's no work. That's also the reason why we used Fs instead of